In the last video, we left off with this graph that shows how the forces change as the distance between two molecules changes. And we see that in general, the attractive force will increase as the two molecules get closer, or atoms, and the repulsive force kind of stays dormant for a while, but then when they get pretty close, it really shoots up. And then I noticed that there was one point in particular that was interesting, and that was when the force, the net force, so it's the attractive plus the repulsive, canceled out. So the force that was pulling the two molecules together was exactly the same as the force pushing them away from each other. And that happened at a distance that I'm going to call the equilibrium distance, or R equilibrium. So now let's also think about potential energy on this graph. So I'm gonna erase the, oh man, I'm erasing a lot apparently. I'm going to erase some of this to clear it up a little bit. And I'm just going to redraw that net force line. It'll look something like that. And now what I'm going to do is I'm going to draw another line, and this line will represent the potential energy. Okay, so this red line is representing the potential energy, which I write as U. And to think about why the potential energy does this, so now potential energy is also up here on the y-axis, I like to think about gravity, and the work we did with work, power, energy will really help us here. When the attractive force is stronger, right, and that's going to happen kind of from the equilibrium distance over. Here the attractive force is stronger. And from here to here, the repulsive force is stronger. And kind of, I guess I should have mentioned this more clearly. I'm kind of assuming in my force diagram that kind of the negative stuff was attractive, and the positive stuff would be repulsive. And we could have flipped it and it would have been fine. And you see that in the previous graph where I drew the attractive and repulsive forces, this black line represents kind of which force was stronger. So if we had a really strong, in the beginning it was almost all attractive force, right? So of course the attractive force would be stronger from far distances. And as it got closer, the attractive force got stronger, but then the repulsive force also started to get stronger and stronger. So when the attractive force is stronger, it's pulling the molecules together. And you can think about it just like two planets that are pulling each other together through gravity. And since there is a conservative force acting on them, right, it's pulling them together as the distance gets smaller, their potential energy will decrease. And you can just think about if I had a ball up here and I let it fall, its potential energy would decrease because of all the work that gravity would be doing on it. So when the conservative force does work on you, you lose potential energy. So when the attractive force is stronger, you're going to be losing potential energy. And then for the repulsive force, it's the opposite. Now the repulsive force wants the molecules to get further apart. But if we start at a far distance and we move them closer and closer, as they get closer, they're going to start doing work against the repulsive force. And when you work against a conservative force, you gain potential energy. And the result of these two things kind of balancing each other out is that red line that shows our potential energy. And the thing that I want you to really pay attention to here is that the potential energy is at its lowest at the repulsive, equilibrium distance, right? So it's kind of negative almost throughout, and it gets positive at the very end, but it's at its most negative at the equilibrium distance. And in the next video, we'll talk about what that means.